please confirm that am I audible?
Yes, sir.
Audible. Okay, then without wasting time, just let's start the session. So, welcome to the second today's session of Operation and Planning of Power Distribution System, whose instructor is Professor Sanjeev Ganguly sir from IIT Guwahati, and I am Satyavikram, a PMRF research scholar from Department of Energy Science Engineering, IIT Bombay. So last session we have seen few of the theoretical concept, like what are the definitions, what are the everything of load factor, diversity factor, and everything. So in this we will solve few of the numericals, small numerical to make the concept basic concept, and also we have few slides related to the second assignment, which will be helpful for you to solving that. So without wasting time, let's start the session. So I will initially give a few basic problem in which you can try to solve and let me know if you face any problem. Okay. So this is the first problem before you try to solve this. I will give you few minutes to solve each of the problems. After that, I will explain that what are the what it actually say and what how it is being solved. Okay. If you face any problem, just let me know in the chat box, or you can open your mic and also you can ask. Okay. Try to solve this. I need answer from everyone. Okay. So that I can be aware that you people know the concept. Yeah.
Sir, it's 900 watts.
Okay, I got a one answer as option B. Okay. Others try to solve. You have 30 more seconds to solve. Okay. That is not a big problem, so we will not waste time on this. And I will explain the concept. After that, we will move forward. Anyone else? Okay, let me explain. Okay, I got option two option B's. Okay, so here the few concept which is being important to solve this problem. One, what is the meaning of okay connected load? Okay, and how it is different from the power which is there at a particular time t. Okay, so when you see the load curve, when you see there is a connected load which is a constant of a particular house. Okay, but that is a connected load, maybe the peak maximum loading you can say of a house, and also the load curve is actually variable. Okay, so this is kind of this is a connected load and this is the load curve of a house, and this is the actually the connected load which is constant. Okay, so at a particular time t, suppose I taken this time as a t, so at this point of time if you have this power at this pt, So this is called as average power. This load curve is having the power which is similar to the connected load. Okay. So connected load means you have a multiple appliances, all the appliances maximum rating what is given at the there on the data sheet, or you have any label which is being written. So here if you see, there are six lamps are there which consume maximum power of 60 watt, plus you have three fans which is connected and consume the 80 watt, and plus you have one refrigerator which is consuming the 300 watt. Okay. So maximum, these are the maximum 60, one single unit consumes 60 watt maximum which is written on its label. Okay. So this will become 360, plus this is 240, and this is 300. Okay. So this will be 36 J8 and 900 watt. Okay. So this is the meaning of the connected load. So here you have understood that what is a connected load and how it is different from the load curve of a particular house. Connected load is constant because it's a maximum peak which can be which is required, and on the basis of this connected load only the meter is being kept by the discom, that we have understood from the last tutorial session. Okay. Discom is distribution company which give you the power and supply to a particular distribution system network. Okay. So this is a solution. There is 900 watt what I have kept. Okay. Try to solve this. This is also a very easy problem, straightforward, but I wanted to give some glimpse and help you to solve the assignments. Okay, option C I got. Option C as a 0.65. Okay. Anyone else? I request everyone to solve that. There are many people who have joined but not giving the answer. If you interact with us, it will be easy to understand that okay, you are getting concept option C. Okay, that's fine. I'm giving you 10 more seconds to solve that because it's a very straightforward formula based problem. Okay. Okay, that's true. So let's solve that. Okay. So here the could you please take some problems? Yeah, it is there. Coincidence factor. There are problems are there. So we will see in the further side. So we are building concept one by one. After that, we move to the higher side of the problem. There is a coincidence factor, diversity factors are there. Okay. So in this problem, you have to understand the connected load concept that I have already explained. So this is a kind of maximum of a host, maximum loading of a, and during a particular day maximum demand recorded was 11.7. Now here are two things are there. Okay, suppose the rating which is given, suppose this is a 18 kilowatt maximum misconnected load was there, it is not as equal to the maximum. Okay. So there is a difference between the different devices. Suppose you have a load lamp load is there. Okay. When it is a comes in a initially it is a very new bulb. Then you see that it consume low power initially, that 11 kilowatt suppose, and then after the time goes on it deteriorates and heating losses increases, that consume more than that, and after that it consume more. So depending upon the derating of the devices, so it started consuming the more power, which most of the power goes into the losses. Okay. So that is a concept that ki here the connected load is not actually equal to the maximum recorded load of a particular time frame. So this can be, and also it can be equal. It is not always that ki it is not always equal. It's sometimes equal. So here also given that ki maximum record demanded means some other time frame it was 18 watt and certain time frame it was 40 11.7. Okay, suppose power at a t1 time it was 11.7, which is a maximum. Okay, and the connected was somewhere at T2 consumed, it was 18. Okay, so it was asking what is the demand factor. Okay, demand factor. Demand factor is basically what is the maximum being consumed divided by total connected load. This is a basic formula, that what is the maximum being consumed at a particular time frame, demand frame, and what is the total connected. So this is a demand factor, means how demand is actually similar to the connected system. Okay, so the maximum was 11.7 and a maximum was 18. So when you divide 11.7 divided by 18, it will come out to be 0.65. Okay, so diversity factor can be equal, means how I have seen that ki this is can be equal to 1 when the maximum is equal to the total connected load, or it will be less than 1. Okay, so this you should remember. What is the definition? Maximum divided by total connected, and it is already always less than or equal to 1. Okay, so 0.65. Okay, try to solve this problem. This is related to load factor. We have seen connected load, we have seen the demand factor, now we are seeing the load factor. Okay, option C I got. Option C, Satri is also there. Okay, I'm giving you 10 more seconds, others also to solve. Okay, let me give the solution. So here when you see what we have already seen, the connected load definition, then we have seen the demand factor. Then we have taken the concept of what is the maximum load of a house. Okay. Now we are moving towards the average and load factor. Okay. So what is the average? Average basically when you have this when you have this daily load curve. Suppose this is the daily load curve of a particular house. So when you see the average power consumption, this is a power versus time. So what is the average? Suppose this is a time block of t is equal to t1, then you have t is equal to t2, and then at a critical time of t is equal to t3 when you have, so different points are there here. Let me take another pen. So they suppose this is certain time, this is certain time, this is certain time. So we have interpolated it and we have plotted this daily load curve. So you have different powers at different time frames. Okay, so the power multiplied by T1, suppose this is T1 time frame of how much duration it is there. Suppose this is certain block is there, no? So this is T1, T1 plus T. So this is difference when you see it is coming out to be T. Okay. So power P1 multiplied by T plus P2 multiplied by T plus dot summation of Pn multiplied by T, whatever the last time frame, and then summation of all the T, means when you're taking T is equal to 1 to 24. Okay, so this is kind of average power. Okay, So what is the load factor? Load factor is basically when you have this all this average powers, then you divide it by maximum, so it is called as a load factor. Okay, so the average here is already given, that is a 150 kilowatt of 24 hours. So 24-hour duration, this is the average being consumed of 150. And what is the maximum? Maximum is 250. Suppose this is the maximum peak, so this is a 250 kilowatt at a particular time frame it here hit it. Okay, so 5355.6. So correct option is point 6, option C. Okay, let's move forward, try to solve this. This is a problem on the diversity factor. Okay, option C, I got one answer. Here all the option, when you see, it is greater than 1. Okay, so diversity factor is always greater than 1. This you should always remember. Let's give few more seconds. After that, I will give the solution. Okay, option C. Okay, I got multiple option C's. Okay, option C. Okay, let's wait for 5-10 more seconds. Okay, let me give the solution. So if you see what is the actually the diversity factor means. Okay, suppose there is a distribution transformer is there. You have a distribution transformer is there, and it is connected to multiple houses. Suppose this is connected to one house number 1, and it is connected to house number 2, then there is a house number 3, and there is a house number 4. Okay, so what is telling that key, suppose four consumers are there, and this is the feeder. Okay, feeder having, this is the 6 kilowatt, and this is 8 kilowatt, and this is 5 kilowatt, and you have other house that is 11 kilowatt. Okay, so when you see this distribution transformer, okay, it is supplying the power which is the summation of all these. Okay, and these are the maximum demands of a particular individual houses. Okay, so when you see what is the diversity factor, basically it sees that in this group, in this all four group, how diverse is the system is. Okay, it means that when you have all these low individual loads are there, how it is different from the what is the maximum demand of the group. Okay, so when you see here the let me explain through here. So we have the individual demands like 6, 8, 5 and 11. Okay, by the definition, when you see, the diversity factor is sum of the individual maximum demands divided by coincidence maximum demand of the group. Okay, so when you see the sum of individual maximum demand, that is 6 plus 8 plus 5 plus 11, that is come out to be 30 kilowatt. Okay, and coincidence maximum demand of the grid is actually 18 kilowatt. What it is already given. So 30 divided by 18 is 1.67, that is already greater than 1. Okay, but when you see that here what is written, the diversity factor accounts for the fact that individual consumer usually reach their peak demand at a different time, so the group peak is lower than the sum of the individual peaks. Okay, what it is telling that in this group, in this overall group, there is a diversity factor that it is it is coincidence maximum demand is of 18 kilowatt, which is very very different than the maximum demand of a individual houses. So you need a one peak which defines the overall system. So we have taken the coincidence maximum demand of the group, that is 18 kilowatt. At a particular time instant it was there. So it was 18 kilowatt. So it's a summation when you do and then divide it by 18, then that you will get the diversity factor of overall feeder. Okay, which is greater than 1. Let's move forward. Try to solve this. If the diversity factor of a consumer, you already know it is greater than 1, so it is given 1.4. And what is the coincidence factor? If you remember the formula which I have given in the last class, yes, option C. Okay. Anyone else? Let's wait for a few seconds. Anyone else? Okay, see, that's true. So, what we have already understood, what is the connected load? Okay, what is the connected load? What is the demand factor? We have seen the what is the load factor of a particular house. Okay, then we have seen the in the last this question we have seen the diversity factor. Okay, now there is a new term which is called coincidence factor. So this is a coincidence factor. Okay, what is the definition of diversity factor? What we have seen, some of the individual maximum demand. Suppose I have taken this is the individual maximum demands and divided by coincidence maximum demand of group. Okay, and it was always greater than 1. Okay, so when you see the coincidence factor, if you have the value lower than 1, so coincidence factor definition is actually 1 upon diversity factor. Okay, diversity factor. If you're defining this here, DF. Okay, and this give a measure that how much individual demands are actually coinciding with the maximum demand of a group. Okay, suppose you have a particular 3 houses and its demands are P1, P2, P3 maximum demands, and their coincidence maximum demand is Px. Okay, so it sees that how much difference is there in between the Px and P2. If Px is equal to the P2, okay, so it says that it is actually coinciding with the maximum demand is coinciding with the maximum demand of a particular house. Same with the P3, that when you see the demand of a particular house and then individual and then group wise, and this also seen as a P1 and Px. Okay, so when you take a particular house and see that how much difference is there in between the average out, not individual means average out of all the houses, how it is different from the maximum and individual maximum. Okay, so when you take 1 divided by 1.4, it will come out to be 0.71. Okay, so here I have also written that the coincidence factor represents the degree of simultaneity of the peak demand. It is always the reciprocal of the diversity factor. Okay, and this is one of the question here. If you have already have the coincidence factor, then how you should calculate the estimated group peak demand? Okay, try to solve this problem. This is an important problem. Try to solve this. Okay, I got B option. Okay. Let me give one more minute. After that, I will give the solution. I request others also to solve. Okay, let me give the solution. Okay. So here, when you see, it is given that there is a transformer, distribution transformer is there, and it is supplying the 15 residential houses. So there, suppose this is a one house is there. So this is house one, and then you have the house two, and then dot dot dot. You have the 15 houses which is supplied from this particular feeder. So each has estimated individual max peak demand of 3.5 kilowatts. Suppose individual peaks are 3.5, 3.5, and 3.5. Okay. So it is written the coincidence factor is zero point 0.6. Okay. And this is a coincidence factor. It is given as the zero point 0.6. Okay. So what we have seen from the formula, okay, the diversity factor. Diversity factor is given as summation of all the houses maximum demands. Okay, means suppose you have I is equal to 1 to 50, so P max I. So this is the all the maximum demand of a particular houses and divided by the maximum of group. Okay, maximum demand of the group. So it he in the question it is already asking the same, that what is the estimated group peak demand. So this you have to find out what is actually equal to this. But here it is given as what is the here it is given in the question what is the coincidence factor. Okay, coincidence factor we already know it is the inverse of the diversity factor. Okay, so diversity factor will be equal to 1 upon zero point 0.6. So it will be equal to, so divided 1 divided by zero point 0.6. So it will come out to be 1.67, or you can write it like this only, 5 by 3. Okay. So 5 by 3 will be equal to all the maximum demand. So here it is already given 3.5. So when you sum all the 15, it will come out to be 3.5 multiplied by 15. And it is asking what is estimated root. Suppose this is x. Okay. Try to solve this. You will 5, 3. It will be 5, 3, 9 multiplied by 3.5. It will come out to be 3.5 multiplied by 9. It will come out to be 31.5. Okay. So it is correct that option B is actually correct. So here you have to just understand that what are the maximum demand of a particular group is there. What is estimated maximum demands of a particular houses will be there. So here the 15 houses are there, and individual peak demands are 3.5. So diverse when you see the summation of all the demands, it will be 3.5 multiplied by 15, and the coincidence factor is already given. So you from that you will find out the what is the diversity factor, and keep that in the formula to estimate the what is the maximum peak demand of that particular group, or you can say of the distribution transformer, which is seen from the distribution transformer. Okay, so here the solution I have already given, that is 13.5. It will come out. Okay, try to solve this problem. This is related to the average daily load. Okay, uh, average daily load you have to find out. This is similar to what we have seen that in that load curve, all the summation of all the power multiplied by time divided by total time. Try to solve, and then from that Try to solve this daily load curve and do the daily load factor. Try to find out. If you get the first answer, just write it in the chat box. The first answer is this. These are the very basic problems, so that's why I kept that to make the fundamental concepts. Okay, I got one answer as first of D and the second is C. Okay, others? Satvik, verify your answer again. So maybe it will be correct, but try to verify again. Okay. Okay, I got Kanchan also given the same answer. Try to verify that. So you should be very clear on that key. It will be correct only. I'm giving 30 more seconds. Others also please try. One and after that I will give the solution. There is a little variation from the option which is shown. Okay, that is no problem. Okay, nearby answers you can give. Okay, that's correct. That's correct. No problem. You can give the nearby answer. That is also fine. Okay, let me give the solution. So in the first problem, suppose this is A part and this is the B part. When you see in the A part, it is given that what is the daily load curve will look like of this 100 kilowatt for suppose this is the 100 kilowatt and this is for the 6 hours. Okay, so this is the 6 hours for 6 hour duration. And then you have the 60 kilowatt and this is the 100 kilowatt. This is 60 kilowatt for next 10 hours. Okay, and then you have 20 kilowatt here for the remaining hours. This is 60 16 4 and this is of the 8 hours. Okay, these are the remaining days. So 10 16 16, then you have 8 remaining. Okay, so this is a power versus time curve. Okay, so this is also a load curve. Okay, so this of the profile is of this particular load. Okay, so let's try to find out what is the average of it. Average will be equal to 100 multiplied by 6 plus 60 multiplied by 10 plus 20 multiplied by 8 divided by 24. Let's solve it. It will be 600 1200 plus 1200 plus 160 divided by 24. It will come out to be nearly 55 point something it is coming, 56.6. So nearly you can say it is correctly nearby equal to 55 kilowatt. Okay, let's try to 1200 plus it was 16 160 divided by 24. It is coming out to be nearly 56.67. So 55 is a nearby answer, so it will be equal to option D is correct. Okay, let's see the B part. B part, when you see, the maximum is already given. Maximum is given as 100 kilowatt. Okay, and we know the load factor is equal to daily load factor is equal to average divided by maximum. Okay, average we have found it out from here, that is equal to 56.67 divided by maximum. Maximum is given as 100. Okay, it will come out to be nearly 0.5667. Okay, that is nearly equal to zero point 0.5, you can see. But here you have to see, be very clear here. This 0.5667 is nearly equal to zero point 0.6. Okay, because when the answers are given in the lower side, you have to take it from the higher side only. So that is a kind of designing factor. So suppose, like, let me take a one slide. Okay, let me explain that. New slide. Let me explain this. Okay, suppose you have this load factor of zero point 0.6, and then you have the average loading is given as x, and the what maximum will be something. Suppose I have taken the m. Okay, from the m you can see some designing constants are there, so maximum will come out to be x divided by zero point 0.6. Okay, this will be the one maximum. Okay, suppose this is a rounded value. Okay, suppose I've taken the this C option zero point 0.5. So this is, suppose this is from the, suppose I taken the higher, and m lower will be equal to x divided by zero point 0.5. Okay. So will be, which will be the higher? Higher will be equal to this. This m lower will come out to be higher in that sense, and the point, this mh will be the lower. Okay, so when you see the maximum demand which is being required, so here your which option should be carried. So our answer was coming 0.566 something dot dot dot. Okay, so which option to be taken? Okay, so when you see the maximum device, maximum side, so here you will consider the zero point 0.5. Okay, this is there is a reason out of that, because when you having the appliances, it having a current carrying capacity. Okay, so when you design a certain system, you always take a higher side of that also. Suppose you have a certain insulation to be kept here, so always you try to take the some safety factor in the insulation design. Okay, so that's why you always take the maximum side of the current or maximum side of the loading. Okay, that's why the option C will be the correct, not option D. Okay, so that's why the maximum loading, the design engineers will be say that ki this much excess insulation will be kept, that will be good. Lower insulation will not be that much good. Okay, that will
Sir, it's
rupture the
option D, right?
that
Point
current
six.
try to flow through the insulation and try to come out to the surface, that okay, that will create the hazard. Okay, try to
Sir,
solve this
excuse
problem.
me, sir. Hello.
No, yes. So in the second part, the option C will be the correct, not option D. That I have told at here now. So we need always at the maximum side of the loading, so that the insulation can be designed in that way, and also the other things also, that you should be higher than that. Okay, I mean, zero point 0.5 is estimated to the zero point 0.6. Okay, no, no, no. 0.56 can be estimated to the zero point 0.6 also, but here the safety side is that you have to see the designing constants also. Okay, when the exact answers are not given, so you should always take the lower side of that, so that you can get the maximum loading values, not the lower side of that. Okay, so that's why the designing engineers will always try to take the safety factor, safety margins out of that. Okay, okay, so I have given the option C. Okay, try to solve this. I will give you 10 seconds only. So we have already seen this problem, this type of problem. Okay. So when you see the demand factor basically we have already seen that what is the total maximum demand divided by connected load. So here also maximum demand divided by total connected. Maximum was 325. Here 325 is already given and 500 was the maximum connected load, total connected load. So when you divide, it will come out to be 0.65. Okay. So the option C is correct. Try to solve this. Okay. Option C, zero point 0.7. Anyone else? Okay. I got C as a two answers. Let me give you more time. Others also let's solve. Okay. 10 second more. Okay. So if when you see here the transformer, there is a distribution transformer is there, which we are seeing here. So this is a distribution transformer, and it is connected to the different houses. So suppose this is a house one, house two, and dot 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 house n. Okay. So it experiences a maximum kVA demand of 175 kVA. Suppose this is experiencing the 175 kVA maximum. Okay, but its rated value is equal to 250 kVA. So it is asking what is the utilization factor of that. Utilization factor is basically what is the actually it is being on which it is being operated, and what is the rated value. So it is already given, it is 175 divided by 250. Okay, the units are same, the kVA and the kVA. So when you divide 175 divided by 250, it will come out to be zero point 0.7. Okay, so here important point to be remember here, that distribution transformer utilization factor is usually belongs to zero point 0.7 to zero point 0.8. Okay, most of the cases. Okay, this is already, you should remember that a 70 to 75% loading is preferable. Okay, that's why I've kept this question. Why? There is a reason that insulation and cooling, these are the two factors which drives that. So when you go above loading 70%, 75, 80, above than that 90, 95% loading, the insulation ruptures, and the cooling methodology which is being used is not sufficient to lower down the temperature in that sense. Okay, so that's why it is being always kept in the 70 to 80. 80 is a very high side, so 70 to 75%. Okay, so this is basically the utilization factor of a particular distribution transformer. Okay, try to solve this. You have to find out the loss factor of the feeder. Option B, I got one answer. Option B. Others also try to solve. Okay, option B, second option. Okay. I got multiple options as a B. So it is correct. It is correct. So what is the loss factor definition we have seen in the last class? Loss factor of a feeder is equal to, this is the average power loss divided by peak power loss. Okay, what is the average? It is actually 12 kilowatt overall day. When you see, this is the average of 12 and then peak was 30. When you solve, it will come out to be 2 6 15 15 4 0. So zero point 0.4 will come out to be okay. So here one important thing you have to see factor of a something. Okay, when you have seen the load factor, then we also have find it out the average divided by maximum. Okay, so when you see this kind of terms like factor of a something, so you always take the average divided by maximum. Okay, so this is basically to compare the average with a maximum. Here also the loss factor is there, so loss factor, the average, then divided by the maximum, that is peak. And same with the load factor also, it is divided by average divided by maximum. Okay, so zero point 0.4 is the correct answer. Okay, let's move forward. This is a one problem related to that. When you have a constant impedance load which is consuming certain power, and there is a feeder voltage drop, that is 0.95, then you have to find out what is the new load becomes. Okay, okay. New load demand, it means that you have a load here, load of 2 kilowatt, and there is a feeder which is feeding to this load, and it is already having the voltage drop in this line. This is the voltage drop is there in the line, which is equal to 0.95. Okay, so when you see from here, from this end, the load which is given to be, that is not 2 kilowatt. This loss is also to be accounted. Okay, so that's why it is asking there what is the new load demand becomes. Okay, okay, I got one answer as option C. Okay, others also, let others also to solve. Here you should always see that this is a constant impedance load. Important problem, important concept is there here. I will give you 2 minutes to solve this. Okay, 2.5 minutes, so that easily you can grasp the concept and after easily solve that. Okay, take your time, think over it, and solve that after that. Just read the problem and try to solve. You will not, if you're not getting the correct answer, that is also fine, there is no issue in that. Just you should thorough understand the problem, then try to read it only. Okay, I'm here to solve that and explain the concept. Okay, option B. Okay, okay. Last 10 seconds also I'm giving. Just think over it. Those who have given the answer also try to check whether it is correct or not. Okay, option C, option C. Okay, okay. Um, Take 10 seconds to re-verify the answer. Okay, let me give the solution for this. Okay, let me first erase this. I will go from basic to basic. Okay, no rush to just solve the answer. Understanding the concept is very, very important. Okay, so there is a feeder. Suppose this is a kind of feeder is there, a distribution bus is there, and there is a line. There is a line is there, and which is having certain impedance. Suppose there is a R and L uh, inside of that R and L, and then you have the particular load is there connected. Okay. So what is given? What is given? Given is that this is a constant impedance load, constant Z load. Okay, and also it is given the power which is it is consuming is 2 kilowatt at rated voltage. Okay, rated voltage. This is very important. At rated voltage, it is consuming the 2 kilowatt. Okay, and then it is written that the feeder voltage drop. It means that suppose this is the voltage V1 here, V angle suppose theta 1 is there, V1 angle theta 1, and here the angle is V2 angle theta 2. If you're not understanding, just this is I am representing of a this particular, suppose this is A and this is the B bus. So A having the voltage at a particular that node is V1 angle theta 1, and V2 it is connected to some, suppose grid is there. So V1 angle theta 1 and V2 angle theta 2. B is having the voltage V2 angle theta 2. So what it is written that delta V voltage drop is equal to 0.95, which is equal to V1 minus V2 basically. Okay. So as far you go from the sending in, the voltage keeps on decreasing. Okay, because the line impedances will be more and more, and the voltage drop will increase further. Suppose you have a particular, this is a generating unit and you have connected multiple loads. Okay, suppose this is a one load, second load, fifth load, and then this is a last load. Okay, suppose this is a V1, this is a voltage here V2, this is V3, this is V4 and V5. So if you wanted to arrange the voltages, which is higher, which is lower, which is midway, so V1 will be always higher, then V2, then V3, then V4 and then V5. And considering that this is a inductive impedances are more. Okay, so that's why the V1 voltages will be higher than this. So as more distance you move from the feeder sending in, the voltage start dropping. Okay, so what is given here that power is 2 kilowatt at rated voltage. So what is the formula of power? It is a V square by Z. Okay, Z it is given thus it is constant. Okay, so when you see the Z is constant, okay, so the Z is constant, it means that V square by P is equal to constant. Okay, getting my point? So Z is constant means that V square by P is constant. Okay, so we are considering continuous reactance and not lumped, if I'm not wrong. So if you consider the continuous also, lumped is basically considering that case summation of all the reactances. Okay, and in between, suppose I am considering that the less voltage, less current is being drawn in between, so you can lump that continuous reactances in a single system. That is a considered as a lumped system. So the drop will be the same, only the minute changes of will be there, 0.001, 0.05, 0.06. This much different if you will observe if there is a not less current is drawn in between. Okay, suppose this is a generating unit and you have a one node here and this is another node and you have a multiple reactances. Suppose this is this and this is like this. Okay, here the load is connected. Okay, So what I am saying that this is A, this is B, and this is C. And here also one load is connected which is drawing very less power, less current. Suppose this is 2 amps and this is 200 amp. So you can lump this also because there is a no less voltage drop in between. Okay, so this current what is coming from here, that is 202 only, and here what is flowing 200 only. So when you see the I square Z loss, I square Z here and here also I square Z, there is no much difference in that. So because the load current is very high. Okay, so that's why I'm considering when you see the lumped sum also, and when you take the individual continuous reactances also, if the current is wrong is less, then the voltage drop will be nominal, that you can ignore that. Okay, so, that is not the focus of this problem. Focus of the problem is that when you have the impedance, constant impedance kind of load, so how you consider the calculate the power if the voltage drop is there in between. Okay, so here what we have seen, the v z is constant and v square by p is constant. So when you see here v square, if the v square by p is constant, so initially you have the rated power, so you have the rated means 1 pu. Okay, so per unit system you already know, no, what is the actual current and what is the rated. Okay, so actual here is same as the rated, so it is 1 divided by p, what it is consuming, it was consuming 2 kilowatt. Okay, so 1 square divided by 2, and it is given when it became the 0.95, if the feeder voltage drops to 0.95. So this feeder voltage which coming here, here at this particular point, it became 0.95. Initially it was 1 because the voltage drop occurred in between. Okay, so that's why the 0.505 drop became inside, and then it became the 0.95, and here you see the point 1 is there. Okay, so that's why the problem is saying zero point 0.9, it if became what is the power it will consume. So when you solve it, it will come out to be 0.95 of square multiplied by 2. It will be 1.80 something. So option B will come out to be nearly correct. Okay. So here also 1.80. So option B will be the correct. Okay. So not option C. Have you got what I am telling? Okay. So when you see at this point, if there is a no drop in between, so if there is a no drop in between, so one will be 1 pu voltage will occur here also, 1 pu will occur here also, but there is a drop is here. So this 1 pu will become some, this will be 1 pu only because it is connected directly to the generating system, and then this 1 pu here at the distribution feeder, it became 0.95. Okay, because of the 0.05 drop in between. Okay, so that's why the if you are having a constant impedance load, so we use this formula, and after that you will find out what is the power being consumed in that. Okay, so when you see it is 1.8. Yeah, this ppt we will say it. Okay, when you see the their portal at the swayam or npta portal, at the end of the bar where you see the assignment lecture 1 lecture 2, at the end you see the presentations. Okay, so teaching materials, so that there you can see this video also, and you can see again this lecture slide as well. Okay, then try to solve this problem. Have you understand the previous problem? If any doubt is there, just let me know. If there is no doubt, just try to solve this. Okay, try to solve this problem. Easy problem but little bit conceptual. Okay, option B, one answer. Others also try to solve. Okay, option B. Okay, I got it then. One answer. Okay, option B. I'm giving you 30 more seconds to solve. Okay, option B. 30 more seconds. I request others also to solve. That will be more good if you try to solve. That will be make your concept very clear. Okay, option B. Okay, that's fine. 10 more seconds. Okay, let me explain. Okay, so what is the definition of load factor? Load factor we have already seen. It is equal to average divided by average power consumption divided by maximum. Okay, this is basic definition. We have already seen that. Okay, and also the what is the definition of average? Average is the equal to, suppose this is per day it is asking, so it is summation of I is equal to 1 to 12. This is a power multiplied by time of that slot, ti pi divided by total time frame, I is equal to 1 to 12 ti. Okay, here what is it is saying that it is consuming 960 kilowatt hour per day. Okay, so the energy is given. Okay, so if you see this part, this is also energy, no? This is energy only. What is energy? Energy is basically what the energy being consumed in a particular day. So there is a 24-hour duration I wanted, so this is power of a first hour multiplied by time of a duration of a particular hour, then p2 t2 plus dot 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 p24 t24. Okay, that is similar only, no? So this is the energy only. Okay, but what you needed, you have to divide it by the time frame, time of the duration. So here it is 24, 24 hours, and it is given 960 kilowatt hour. Okay, when you divide it, it will come out to be, this is 24 hour, so 960 divided by 24, it will come out to be 40. So average came out to be 40. So what is the load factor? If you try to calculate, because the maximum is already given, it is 80. So it will be 40 average divided by 80, it will come out to be 0.5. So correct option is option B. Okay, that's true. So here the only you have to understand that in the average, if energy is given, from that also you can calculate this. Okay, try to solve this. Very easy problem, just from the previous things we can you can solve that. Okay. Option B and C. Okay, option B and option C. We will not waste time on this, so I'm giving you 20 more, 20 30 seconds to solve this only. Any other answers? Anywhere? Okay, let me give the solution. So this is very simple problem. You already need know that what is diversity factor. It is actually the summation of all the powers of individual houses, then divided by what is the coincidence maximum demand. Okay. So non-coincidence maximum demand of a group is 200. Okay, it is already given. This is a non-coincidence. It means that it is already the summation is already given. Okay, so divided by 140. When you try to solve, it will come out to be 1.5. 21 divided by 14. 1.5. So the option C is actually correct here. Okay, so the diversity factor will come out to be 1.5. And what is the coincidence factor? Coincidence factor is inverse of that. So when you divide 1 divided by 1.5, it will come out to be 0.67. Okay, so the option B is correct here. So C comma B is correct. So it is easy problem. You just have to know that what is diversity factor. It is non-coincidence maximum demand divided by coincidence maximum demand, and coincidence demand factor is the inverse of the diversity factor. Okay. Try to solve this. This is also important. This is from the feeder side, which we have seen, and then after that, this will be the one problem. Okay. Try to solve, and after that, I will give the answer. So it is written here that you have the uniformly distributed radial filter. This uniformly distributed radial filter is very very important, and the total length is given 6 kilometer, and sending in current is 240 amperes. The current at a zero point 0.2 kilometer from the substation. So this is suppose this is substation, and you have this feeder, and this is the receiving radial feeder, and then you have this a 6 kilometer. This is okay. So it is given that the injection current is 240 amps. It is asking if it is a 2 kilometer, what will be the current? If it is a 2 kilometer here. So here you have to find it out here at this location L. You have to find out what is the current. Current will be there. If there is a uniform distribution will be there. If you don't understand the problem, just let me in the chat box. Okay, I will directly jump to the answer part. We will not waste on the uh, I'm giving 10 more seconds. After that, I will give the answer. Okay, C, I got one answer as 160. Okay, you also have to understand that why the current drop will be there at a particular uh, point at a particular length in the distribution uniformly distributed radial feeder. Okay, let me explain this. Okay, option B. Okay, so option C is actually correct, 160. So here you have to understand that length is given to 6 kilometer, is given 260 at a sending in, and x is the 2 kilometer weight is been asked. So there is a formula, you have to remember this. The ix, that current at a particular length will be equal to ix. Suppose the ix x length is equal to is, what is being sent from the sending it, will be equal to 1 minus x by l. Okay, so through the length the current will drop. Here it will become 240. 1 minus, it is being asked 2 kilometer divided by 6, it will come out to be 160. Okay, through also you can see here, from here also, that 240 for 6 kilometer it is there, no? So what will be there at the for the 2 kilometer? 2 kilometer, it will be 240 divided by 6 multiplied by 2, it will come out to be 23380. Okay, so here if you see, it is wrong. Okay, why? Because when the you see the 80 ampere drop, it will not from the this side. Okay, it will drop from the 80 amps. Okay, so that is being asked from here. So it is from here. When you have calculated through this means, it is from here. So here it is saying that the 80 drop has happened. Okay, so 80 ampere will be here pointing out. So that's why the when you subtract 240 minus 80, it will come out to be 160. Okay, that's why in the problem, in the solution, when you see, it is 1 minus x by l, not is multiplied by x by l. Okay, when you're seeing from the substitution side. Okay, try to solve this problem. That is similar, that it is also uniformly distributed. What is at the midpoint of the feeder, what will be the current? Yes, that is correct. That is also we have seen that I formula ix is equal to is 1 minus x by l. X is equal to l by 2. When you keep it here, it will come out to be 0.5 is. That is true. Okay, option C is correct. Okay, so just you have to remember this formula. You can put it and get the answer. Try to solve this. It is written that there is a uniformly loaded feeder is there, which is having resistance of 0.25 ohms per kilometer, length 4 kilometer, sending in current is 160. You have to find out what is the power loss. Okay, option B, you got one answer. Okay, option B, that is true. Let me see what is correct. 25 point TPM. Okay, I have to solve it. Okay, let me solve. Okay, what it is given here, it is given that r is given as 0.25 ohms per kilometer, length is given 4 kilometer, is is given 160 amps. So in the radial feeder with uniformly distributed load, total power loss will be equal to 1 by 3 times of is square rl. So here I am not going into the definition part you can see from your end. Okay, okay, so it will be equal to 1 by 3 is square. Is square means 160, and then rl is given 0.25 multiplied by length 4, so it will come out to be 1 by 3. Let me solve. 160 of square multiplied by 0.25 multiplied by 4 divided by 3, it will come out to be 8.53 kilowatt. Okay, so the correct answer was okay, is square r multiplied by l. Okay, sending it distributed, so it was coming 8.53. I think all the answers are actually wrong. TPL, total power loss. Okay, 8.53 will be the correct answer. Okay, multiplying by 4, I think. We'll go 34. No. So this is of a particular per unit length. Okay. So this is total power loss per unit length, because R we have used of a 4 kilometer, then we have used the 0.25. Okay. So this will be a total power loss 8.53 kilowatt will be come out to be. Okay. So you just have to remember two formulas. It is giving 8.53 total power loss, and also from the sending in what will be the power miscurrent drop will be there. There are two formulas will be there. Try to solve this. What will be the total voltage drop? Now you have to see the what is the voltage drop will be there. Okay, option C. Okay. There is one formula. You just have to see that the delta V voltage drop formula will be half of ISZL. Okay. So the ZL Z is given 0.5. That is correct. That option 125. 125 means option C is actually correct. So VD will be equal to half times of ISZL. So half will be the ZL will be 5 multiplied by zero point 0.5. It is already given 2.5 will become VD is equal to half multiplied by IS is given 100, and this is 2.5. VD will come out to be 125. Okay. You don't have to go into the depth of that. You just have to remember few of the formula, like IS drop will be there at a particular location. What will be the power loss? What will be the voltage drop? Okay. Try to solve this. This is not 1 by 4. This is actually the I by 4. I by 4, I by 3, I by 2, and 2 I by 3. I'm giving 10 more seconds to solve. So this is little bit complicated, but not that much. Okay, let me give the formula for this. So here you already know that ki VD is equal to half ISZL. C. C is actually correct. That is L by 2. Okay. So it is given lump load. Lump load means ki this will be equivalent to the when you have the radial feeder which is in uniformly distributed. So current decreases linearly from the sending into receiving end. Okay. So the same voltage drop which you experience, the total voltage drop turns out to be same as the entire load when the lump is 1 point along the feeder. So it will be at the midpoint, center of that. Okay. So the equivalent have the same voltage drop which is at the midpoint. Okay. Try to solve this. This is also I by 4, I by 3, I by 2, and 3 I by 4. So here it is asking when, at which place it will be same power loss will be there. Okay, let me explain this. So when you see the what is at which point it will be the maximum power loss will be there. Okay, so it is saying that radial feeder, which is uniformly distributed. So you just have to remember that he at the L by 3, not L by 2. Here I have already written here. So it will be assumed that the power loss will be there, maximum will be at the center. That is not the correct. So it will be higher at the L by 3 location. This is through the formula you can see that at the derivation in. Here you just have to remember few of the things. Okay, so here I have kept few of the problems also here, that at which location it will be effectively the increasing factor will be there, and then few of the problems like where the same voltage drop, if the voltage doubled and the feeder length is double, what will be the new loading will be there, and the different problems related to the line current which is closest to. Okay, when you having try to solve this problem. I will solve few 2 3 problems, and after that I will give there that key. So I will show that ki how much different problems will be there. I will give you to solve from your side. Try to do 2 3 problems from right now. Okay, B, I got one answer as in option B. That is actually correct. Here, a few of the things you have to just remember that in the uniformly distributed feeder, you have the voltage drop will be there in the line, current drop will be there also at a particular length, and also there will be a power loss will be uh, a power loss will be there in the system. So the real power when you delivered, when you see this is 900 kVA will be it is given. So this is yes basically, and the power factor is given 0.85. Okay, so you already know power is equal to S cos phi. This is one formula. So you already power is S is equal to P plus JQ. Okay, so the cos phi S is already given 900 multiplied by 0.85. It will come out to be 765. Okay, kilowatt. Okay, that is correct, 764. Line to line voltage. So here I have kept few of the problems, and I will request you to solve from your end. And if you're facing any face any problem, just let me know in the next tutorial session. We will try to find it out how it will be solved, and how what will be the correct way to approach that. Okay, that's all for the today's. Is there any problem? Just let me know, and after, otherwise I will end the session. Okay, in the next tutorial session we will try to solve few more problems, and this we will upload. Okay, video also, and also this presentation. Any doubt? The PPT you will get on the portal itself. Okay, so when you see the SWAM portal at the end, so in end of the bar, where you see that assignment section is there, and then after that you have the print lecture slides and different materials are there, no? So at the end where you see the videos and the feedback form, the above of the feedback form there is a link of these slides is there, so you can directly click on that and you will see the slides. Okay, so that's all for today's session. So thank you so much for joining.